Hello, good morning everybody. Have a seat. So my name is Heunen. I'm very happy to be here. It's a real pleasure to be invited. I think you feel like a big boy and shed some of my imposter syndrome. I'm going to be talking today about something that several of you have already heard about. Parts of the talk have been used before, and I'm sorry about that. But I figured if I'm going to give a keynote speech at a category theory conference, I should use this as a platform for some sort of sales pitch. So I'm going to pretend I'm a car salesman and sell you on something called Dagger category theory. We heard a bit about this yesterday. So Dagger categories are a bit like ordinary categories, but they are self-dual in a very strong way. We'll get to the definition in a minute. They have been used in literature in various ways. They've been called inherited categories, or star categories, or bar categories, or categories with an evolution. I'm not sure the term Dagger is totally appropriate, but I think it's stuck now and you have to deal with it. It kind of works. And my goal today is to convince you that category theory is all good and well, but Dagger category theory is where it is. There's a very interesting interplay between the two. You can study Dagger categories through the lens of like an ordinary category theorist, but there's more to it than that. And it's not just formal category theory or rich category theory, it's really a different kind of thing. And the theory is different from ordinary category theory in some sense. I mean, you can compare it a bit to graphs. In graph theory, you can have a subsection that's about undirected graphs, and you have subsections about directed graphs. Now, you could say any undirected graph is just a special kind of directed graph, where you have edges going both ways to emulate one undirected edge. But there's honest differences in the theory too. For example, if you think about chromatic numbers or something, the theorems are really different if you talk about undirected and directed chromatic numbers. Same kind of thing happens for analysis. You can do real analysis, you can do complex analysis, and you could say complex numbers are really just pairs of real numbers that multiply in funny ways. But that's sort of missing the point, because if you think about, let's say, differentiable functions, in real analysis you have differentiable functions. In complex analysis you have holomorphic functions. But in complex analysis they're much more constrained for some reason, and the theory is much more rigid, and at least different than the real case. And the point I'm going to try and make is that in category theory and Dagger category theory you have the same kind of relationship, a sort of directed and undirected version of each other. You could think of a Dagger category as a category with some extra structure on it. But that's missing the point, because the interesting things about Dagger categories, you should be thinking them as a primitive thing. So that's my goal for today. I'm going to do that in 4 acts. I realise a classic drama play has to have 3 acts, but we're not going to have, an emotional arc like that, sorry. But if you think about a hypothetical category theory textbook, you might start with thinking about categories, then you might go on to something like monads, you might progress to something like limits. We're going to try that kind of tack. We're going to do the same thing, but then put Dagger in front of everything. Now last act I'm going to talk about my favourite Dagger category, which is a category of Hilbert spaces. And we're going to see how you can characterise that as a Dagger category, and the Dagger plays a crucial role there. So that's the plan. Let's start with Dagger categories. What are these things? We saw them yesterday already a bit. So a Dagger on an ordinary plane category is a contravariant functor that does nothing on objects, is identical to objects, and is involutive. So if I do it twice, I end up with the same thing I started with. So if you have a map F from A to B, then F daggers a map B to A in the other way, and flipping it twice doesn't think. This is not any kind of enrichment as far as I know of. Hom sets are still just sets. They don't have any special extra structure, but it's more about the relation between 2 different Hom sets, Hom AB and Hom BA. It's also not some kind of formal category theory. Well, I'm cheating a bit there. You can think of it as formal category theory inside the category of Dagger categories, but that's sort of missing the point, because as we'll see in a minute, that's sort of pushing the problem up one level, and you're not really solving the problem. If you see this definition, you might think, as I was trying to suggest earlier, that a Dagger is an extra structure on a normal category. And that's true. One category can have several Daggers on it. But I'm going to take the point of view that you should think of it more as a property. We're going to take Dagger categories as their own primitive thing. It has an underlying category, fine, we can use that, but the Dagger is integral to everything. And that translates into something called evilness on the MLab. You might think this is an evil notion because I'm talking here about objects being equal to other objects. And a proper category theory shouldn't be doing something like that because it's not stable under equivalence of categories. Peter Challenger, who actually coined the term Dagger categories, has a no-go theorem saying that if you have an equivalence of categories, one of them has a dagger, there's no possible way of putting a dagger on the other one so that it's preserved under the equivalence. And that's a valid proof is correct, of course. But you can quibble a bit with it, because he's taking the ordinary the ordinary category theory point of view. Peter Lumsden has a different take on that. He says he's thinking not about categories, but about categories with an embedded subcategory that's sort of fixed. And if you take that point of view, this no-go argument goes away. I sympathize with that, but I think both of them are moot. The point is you think about Dagger categories, period. Right, so that's the definition. Now I'm going to give you loads of examples. First example is take your favorite involved line. For example, you can take the complex numbers under multiplication. The dagger on that would be complex conjugation. Or a different example, you can take your favorite involved ring R and look at n by n matrices over this. Of course, this is a moment because you can matrix multiply two matrices. And it comes with a dagger because you can take the conjugate transpose of a matrix, and if you do that twice, you end up where you started with respect to multiplication. So these are sort of one object dagger categories, and any one object dagger categories is just an involved moment. You can take any groupoid. So you can have many objects, but every map has an inverse, and the dagger is the inverse, because of course the inverse is also something that goes the other way. As I was saying, a groupoid can also be a dagger category in a different way. The dagger doesn't have to be the inverse, but the groupoid will be like this. A somewhat more general case of this is not if every morphism has an inverse, but if it has a partial inverse in the sense of inverse category. Which is defined to be, for every map there's an F dagger in the other direction such that you can sort of undo F. Sometimes these things are called partial isometries. And the very next talk, Robin Cockett will be talking about something related to that. You might not mention the word dagger, but it is there. And you can ask him about it. Oh no. A different type of example that we saw yesterday already for a bit is the category of sets as objects and relations between sets as morphisms. So by relation, I mean a subset of the product of A and B. And of course, if I have a relation from A to B that tells you these elements of A are related to these elements of B, then I also have a relation in the other direction because I know these elements of B are related to these elements of A, and I can swap that twice. And that you can generalize that in various ways. You can start with any regular category, take the relations in that will carry a dagger. You can take any allegory, that will carry a dagger. Or, if you are so inclined, you can take the quantile and look at Q-valued relations. So these kinds of relations are sort of matrices of zeros and ones, if you like. You can put entries from a quantile instead of the zeros and ones in the entries of your table. And in fact, this afternoon there will be talk by Heunen and Mobius that I think goes a bit in that direction. More examples. If you start with any category of pullbacks, you can look at the spans. So the objects are just the same as the objects of C, but the spans are, spans in C. Of course, if I have a span, I can swap it around, and that's the dagger. And similarly, I can turn everything upside down and talk about whole spans. On the previous slide, we had a one-object version of matrices. You can do that for any number of objects. So I can make a category, the objects are natural numbers. The morphisms from, let's say, A to B are A by B matrices with entries in some involved ring. I can still take the conjugate transpose to go, from B to A. You can take this infinite dimensional, if you like, because in this example, you have finitely many rows and finitely many columns. You can make that infinite, and you can talk about the category of Hilbert spaces, and we'll talk a lot more about this later. I'll go into the definition of what a Hilbert space is later, but it's possibly infinite dimensional vector space with an inner product on it. And specifically, it has a property that makes sure that if you have any map F, there's a unique adjoint satisfying this, and if you do that twice, that's automatically the same as just doing f. You can choose whether you want continuous linear maps, or you can take linear contractions, or you can take other kinds of maps. And this can be generalized too. You can think about multi-Hilbert spaces over complex numbers, for example, with Hilbert spaces over a Z-style algebra, and they're called Hilbert modules. And basically, these things are sheaves over some space, topological space X, whose fibers are Hilbert spaces. So that's another class of examples. Next class of examples, you can take free and co-free Dagger categories. If I start with an ordinary plane category, I can make it into a Dagger category in these two ways. I can make the co-free one, where I keep the same objects, but a morphism in the new category is going to be a pair of morphism in the old categories. So this is a bit like making an undirected graph out of a bidirected one. It's sort of obvious how you propose two such things. And of course I have a Dagger now because I can flip the two elements of one morphism. That will go the other direction. And in some sense, this is the smallest, well, it's a free way, co-free way in which you can make a category into a Dagger category. More specifically, there's categories, Dagger categories that we'll get to in a minute that are called cat. There's a forgetful functor cat, because every Dagger category is an underlying category. And this construction is the right adjoint for that. There's also a left adjoint, where you start with a plain old category. I'm going to make it into a free Dagger category in the following way. Still going to take the same objects, but this time a morphism from A to B is going to be a zigzag of morphisms in the old category. And then I'm going to subject to an equivalence relation that says this zigzag, whenever I see it inside the big one, is the same as that one. So it's roughly saying the way you compose two such zigzags is just by juxtaposing them. And if you have something in the middle that ended with an identity, then I might just as well have composed these two bits. Stands for reason, I would think. And the same the other way around. And in fact, you can prove that this is a left adjoint to the forgetful functor from Dagger categories from Dagger categories to categories. So there's many examples, is the point. Now let me go slowly into more of the structure of these things. I was talking about Dagger categories and adjoints to the forgetful in the previous slide, but what is this category, Dagger categories? So the next definition is, if you take your hypothetical for category theory textbook, you know what a category is, what is a functor? And the obvious thing to ask for is a Dagger functor. I'm going to just put Dagger in front of everything like an, sorry, I don't know my English, that's an adverb, adjective, thank you. It's just an ordinary functor that preserves the Dagger. So taking Dagger first and then mapping it across is the same as mapping across and then taking Dagger. This forms a two category, in fact, that we'll call DagCat. If you take Dagger categories as 0 cells, Dagger functors as 1 cells, natural transformations as 2 cells, I don't have to say any Dagger for natural transformations, because if you have any natural transformation, then taking the component-wise Dagger is again automatically natural. And that's sort of interesting to see, so you get a feel for that. This is what naturality means, right? I map some F, and I intertwine it with components of a natural transformation. If I take the Dagger of this whole square, all the arrows turn the other way around. But F is a Dagger functor, so taking the Dagger of FF is the same as first taking the Dagger of little f and then doing big F. So, and every morphism in here arises that way. So in other words, alpha Dagger is automatically natural. And in fact, this is showing it's not just a 2 category, but it's a DagCat enriched category. And that's what I meant by you just pushing the problem up. This gives rise to even more examples. So if you have 2 Dagger categories, you can now look at the category of Dagger functors from the one to the other, with natural transformations between them. That's again a Dagger category. Specifically, interesting case of this is we saw that any group is a Dagger category, so Hilbert spaces is a Dagger category. If you take the functor from one to the other, that's exactly the unitary representation of that group. And maybe a slightly more interesting example, and that's my last example for now before we get into theory, is I can take as objects Dagger categories, but I can take more interesting arrows between them. I can take functors, contravariant functors from the source to the target, that I demand have a right adjoint. It doesn't matter if I say left or right because of the contravariance. I'm going to take them up to natural isomorphism. So these are the morphisms. It's slightly complicated, and maybe it helps if I tell you that the identities are the dagger on the object itself. And how do you compose through such things? You do the contravariant functor first, you use the cell duality, you do the other contravariant functor. That's the fine category. And in fact, of course, it has a dagger, because if I have one such thing, it's guaranteed to have an adjoint, and the adjoint is something that goes the other way. So contravariant, and if I do it twice up to natural isomorphism, it will be the thing you start with. So that's sort of interesting, but we're not going to use it for the rest of the talk. Alright, that's all the examples so far, and that brings us to the end of Act 1. Now let's go to Act 2. So the theme that's starting to come out is that whenever there's a dagger in sight, whenever there's a dagger present, everything inside has to cooperate with a dagger. And this is sometimes called, this is the philosophy of dagger categories, and it's sometimes called the way of the dagger. And that's what they teach you in martial arts. If somebody points a dagger at you, you cooperate. You run away, you give them your wallet, just work with it. And that goes specifically for various kinds of morphisms inside the dagger category. We're often not going to be interested in monomorphisms, what's called dagger monomorphisms. So these are monomorphisms that are not just split, but split by their own dagger. Same for dagger epimorphisms, they're split by their own dagger. Dagger isomorphisms, they're not just invertible, but they're invertible by their own dagger. Dagger idempotence is another thing we're going to see. So it's not just that the morphism is equal to its square, but it's equal to first F and then F dagger. So going forth and going back, if you like. So these are special kinds of morphisms, but also if you have structure on your category, let's say a monoidal product, we're going to say that it's a dagger monoidal structure, when first taking tensor product and then taking dagger, it's the same as doing it the other way around. So basically everything has to cooperate with the dagger. The same kind of thing you might think goes for, that we did for functors. You might think we should do that for our junctions too. But you don't really need to, because if you have two dagger functors, F and G, F is left adjoint to G, then automatically G is also left adjoint to F. It's relatively easy to see. Suppose you have a natural bijection phi between this homestead and that homestead, then I can make a natural projection going the other way by taking a morphism from GD to C. I have to produce from D to F of C. What I can do is first take the dagger, so now it's going from C to G of D, something of this type, match it across, and then turn it around again. So a junction sort of automatically play nice with the dagger. Equivalences, though, are a different kind of thing. So we can talk about isomorphisms, or dagger isomorphisms and dagger, but they're sort of too strong. And you might want a dagger version of equivalence as well. So we're going to say that two dagger categories are equivalent, F and G are equivalent if you have functors up and down, such that their composition is not just isomorphic to the identity, but dagger isomorphic to the identity. And now I can quickly come back to what we were saying earlier about evilness. So to prove two things I'm going to point out and not say a lot more about. That if you have an ordinary adjunction, one category has a dagger, and going around one time is a dagger isomorphism. Then there's a unique dagger on this that makes this into a dagger equivalence. So in special cases you can transfer the dagger across in a unique way. And the other thing I'm going to point out is that this is sort of there's several definitions of equivalence usually. One is in terms of adjoints, one is in terms of this, natural equivalent, natural isomorphisms, and the third is in terms of full and faithful functors. There's a similar kind of thing you could do for dagger categories. If you have an ordinary functor, but D this time has a dagger, F is full faithful, and not just essentially surjective, but dagger essentially surjective, meaning that any object in here is dagger isomorphic to one coming from there. Then you can pull the dagger back to here in a unique way to make the thing into dagger equivalence. And I think this is sort of the right way to think about dagger categories. You should think about these kinds of equivalences.
Sorry, just to be sure, I understand. Dagger natural isomorphisms are component-wise Dagger isomorphisms.
Yes, correct. Well done. Any more questions at this point? Yeah.
Is there an equivalence between Dagger equivalences and full faithfulness and Dagger established?
Yes. That's roughly what the third point is saying.
Okay.
Yeah.
Is part of the point that you were making earlier that these are not just the two categorical notions internalized to the two category of Dagger categories, like you have to define these in a direct way to get the right notions?
I'm not exactly sure, but I think so, yes.
Okay.
I can't think on my feet well, but let's say it's yes for now. You can crucify me later if it's no. Alright, now we're going to move to Dagger monads. So, chapter 2 of our category theory textbook, we learned about monads. How do these things cooperate with the Dagger? I'm going to claim, here's a definition for what the Dagger monad should be, and then I'm going to give you pieces of evidence, and you can be the jury whether it's the right way. So I'm going to say a Dagger monad is an ordinary monad that's also a Dagger functor, so it preserves the Dagger as a functor, satisfying this funny looking law. This is called the Frobenius law, and that's the Frobenius. If you write it out in terms of its types as a diagram, it goes like this. You start with an object A, you apply the monad twice. There's two things you can do. First thing you can do is you can take the Dagger of the multiplication. So you insert one more application T, and then you can do T of mu. The other thing you can do is T of the Dagger of the multiplication. Also inserts another copy of T, and then multiply. So it might look a bit funny, but I think that's the right thing to do. One example of such a thing is that some people that have seen string diagrams in monoidal categories might be aware of is if you start with a monoid in a monoidal category, and I'm drawing this for the multiplication, multiplication. In a Dagger monoidal category, it also is automatically a co-monoid and has a co-multiplication. If I call that monoid B, then blank tensor B is going to be a monad. And it's going to satisfy this law exactly when this string diagram equation holds. And this is what's called the Frobenius law in algebra. So that's where the name comes from. Another example of such a monad is if you start with a Dagger adjunction as we had on the previous slide, you go round trip, that will be a monad, and it will in fact be a Dagger monad, so it will satisfy this law. So that's the first piece of evidence. It works well with Dagger adjunctions. Okay, second piece of evidence. Suppose you accept this definition. Let's think about Kleisli categories for these things. I claim that if you start with a Dagger monad, then its Kleisli category automatically has a Dagger again. And I think it's instructive to see how that works, so I'm going to take you through that. So we will sort of see the Frobenius law appear in here in a minute. That's sort of circumstantial evidence, if you like. There's also a way to derive the Frobenius law from first principles as a coherence between the Dagger and some sort of closure, but I don't have time to do that. So this will have to do for the jury verdict. Okay, how do you take the Dagger? You start with a Kleisli morphism, so that's a map from A to T of B in the base category. What is its Dagger? We need to produce a map from B to T of A in the base category. I can take the Dagger in the base category of F, that will go from TB to A. I can apply T to it, which gets me this far. And then I just need to get from B to T squared of B, which I can do with monad structure. So first do the unit, then do the Dagger of the multiplication. Right? This, yeah?
If F adjoint left element to G implies G adjoint to F, and if you have a monad, you also have a comonad structure, right? Does that satisfy some sort of Frobenius law?
Yes, it does. So we'll get to that in a bit. There's a very strong sort of self-dual flavor to everything. So everything I say about monads also holds for co-monads. And later when it comes to talk about limits, everything I say about limits is also going to hold for co-limits. So what do I have to prove? That if I do this recipe twice, and you end up with the same thing. So you start with A, you do this recipe, and over there you do the recipe to the recipe. So this here is in the base category what F double Dagger unfolds to. I'm going to show this equal to F. First square here is just naturality of the unit. Second square here uses naturality of the multiplication and the fact that T itself preserves daggers, so that this is again a naturality square. This square over here is the Frobenius law. That's literally what it said. Here's another naturality square for the unit. And now we notice over here that if you first do the unit and then do the multiplication, and then, where did they go? Unit multiplication, T of dagger of unit, that's the same as just doing T of dagger of unit. So that's done. And now we have here the dagger of first doing the unit and then doing the multiplication. That's the same as doing the identity. So all in all, this F double dagger is equal to F, which is good. And you sort of see where the Frobenius law comes into play. So it's not a foolproof proof, but I think it is good circumstantial evidence that it's right in the law. And that's kind of replacing. Alright, we had Kleisli algebras. What about a little bit more algebras? And again, to satisfy the way of the dagger philosophy, you have to put something in front of the algebras, because not all algebras are going to be nice. And I don't want algebras that satisfy the Frobenius law themselves again. So we'll say Eilenberg-Moore algebra is a Frobenius Eilenberg-Moore algebra when it satisfies that square, which is roughly the same as the Frobenius law, except that now I've replaced the multiplication by the algebra, the structure map of the algebra, and in pictures it looks like that. Let me give you some examples of these things before I present you the circumstantial evidence that this is the right law. First one, any free algebra, so something of this form, will automatically satisfy that, because that's literally what the Frobenius law said. So specifically, there will be an inclusion of the Kleisli category into the category of Frobenius Eilenberg-Moore algebras. Then I have two examples based on Hilbert spaces. Take your favorite number n, look at C to the n, take A to be the algebra of n by n complex matrices. Then, as we were saying, that thing is a Hilbert space itself if you put right angle product on it. So it is a valid monoid in the category of Hilbert spaces. And you can tensor with it, so that Y tensor A becomes a monad, and it's in fact a dagger monad. And I can make an algebra for A itself. So the structure map takes something in T of A, so it takes two matrices F and G, and produces a new one. What do I do? So multiply them, but first I conjugate G with a fixed dagger isomorphism. That's always going to be an algebra, but it's only going to be a dagger for the Frobenius algebra, satisfying that law, when this dagger isomorphism is self-adjoint. So not all Eilenberg-Moore algebras are Frobenius Eilenberg-Moore. Third example, and last example, if you start with just C to the n, as a vector space, call it B, I can again build a monad by tensoring with B. Then, if you work through what it means to be an algebra and you unfold all the rows, you find that giving an algebra is the same as choosing n many dagger idempotents on the space that the algebra lives on. That add up to 1. In quantum computing, quantum information theory, these things are called projective quantum measurements. So it's sort of an interesting real-world kind of example. Okay, so those are examples of dagger Frobenius-Moore algebras. Then again, why is this the right law to put on an algebra? I can prove two lemmas and then a theorem. The lemmas say that if you have a dagger on base cat 3, you have dagger monad to look at dagger algebras, that's again going to have a dagger. Second lemma says that the structure map for an algebra itself is going to be, so its dagger is going to be a homomorphism exactly when the algebra satisfies Frobenius law. And if you compose the two, if you use the two lemmas together, you will find that whenever you have a dagger category C and a dagger adjunction on it, so in other words, a dagger monad on the category C, you can look at the Kleisli algebras, there's a dagger adjunction to there. You can look at the Frobenius Eilenberg-Moore algebras, there's a dagger adjunction to there. And these are the extreme two cases. This is the initial one, that's the final one, and there's always going to be comparison Dagger counters that make everything commute. So I think this is strong evidence that this notion of Dagger monad is the right one. Alright. Act 3, Dagger limits. Let's move away from monads and think about limits in chapter 3 of our technical textbook. Let's start with something very simple. A terminal object. This is a very easy kind of limit. In a Dagger category, if you're terminal, you're automatically also initial, which means you're a zero object. And similarly, if you talk about not nullary products, but binary products, you're going to say a product is a Dagger product if the two projections are Dagger epimorphisms. But moreover, and this is an important one, they're sort of orthogonal in some sense. If I do the Dagger of the one projection and then the other projection, I want to get the zero map. So that's the definition of Dagger product. In the category of sets and relations, these things exist for any two objects, and you can take disjoint union of sets. In the category of Hilbert spaces, you can take direct sums, and there's not just direct sums but orthogonal ones, and that's what this condition is saying. Next thing you might think is, good, I know what products mean, what does Cartesian closed mean? Does a Dagger play nicely with that? And this is one example that's very easy to see, but it's one example where Dagger category theory is really different from category theory, because there's no such thing that doesn't degenerate. If you're Cartesian closed and you have a Dagger, then every home set must be a singleton. You're the indiscrete category. Here's a very simple proof. Look at a home set. A, of course, is the same as 1 times A. You're closed, so I can take the A over to the other side. But 1 was terminal, but it's also initial. So there's a unique map from 0 to anything. Right, so Cartesian closeness is just not a good notion in the Dagger setting. Okay, continuing with limits. We know about products. The next thing you might ask is, what are products? I claim this is the right notion. Dagger equalizer is just an ordered equalizer, which means that the cone map is automatically monic, but I don't want it to be just monic. I'm going to demand that it's Dagger monic. And similarly, Dagger kernels are things that I can kernels that are Dagger monic. These things exist in the category of Hilbert spaces. If you take two arbitrary maps, they're equalizers, literally created by the forgetful set. And the point is, this is a closed subspace. That's what this Dagger monic thing is saying. In sets of relations, kernels, Dagger equalizers do not exist, but at least Dagger kernels exist. If you have any relation R, you look at all the things that are not connected to any other element of the codomain by the relation, and that would be the Dagger. The inclusion of that would be the Dagger kernel. And just having Dagger kernels in itself is already quite interesting, because that gives a lot of structure to the category. Paolo Broni was saying this yesterday to some extent already. If you have Dagger kernels, then you can look at, for any object, the kind of sub-objects, the Dagger kernel sub-objects, of all the kernels going out of that object. This will be a pole set. And in fact, the pole set has more structure than that. The order structure is just as you'd expect, one kernel factoring through another. But you also have something called an orthocomplementation on this pole set. So any kernel comes sort of with a partner, with a complement, that you can compute like this. You give me a kernel K. I'm going to take this Dagger, something out of A, and I take the kernel of that again, which is something into A. And I'll call that K complement.
Sorry to interrupt. Can you repeat what the definition of Dagger monic was?
Yes. That means, sorry, quite a while back here, over there. So it's a monic that is split by its own Dagger.
Oh, so
you go forward, you go back, nothing happened.
Okay.
So if you think about Hilbert spaces, that means it's an isometry. There's an embedding of the small thing into the big thing that preserves distances.
We'll call it a Dagger section.
You could call it that. So really that's another remark. Sometimes I might say isometry instead of Dagger monic, and I might say unitary projection. So the terminology can be borrowed from various places. Dagger section is perfectly fine. But for the sake of the talk, I try to say Dagger monic everywhere. Very well. Right. So this kernel whole set attached to an object is always an orthomodular lattice, in the sense that you can take this complement, doing it twice does nothing. It's antitone, it's real complement, and satisfies what's called the orthomodular knot. So it's not distributive, but a weaker version of that. So quite some structure, just from Dagger kernels. Okay, so now we have some specific instances of Dagger limits. Here's my definition, sorry, not quite yet. I want to give a definition of what a general Dagger limit should be. What should this thing look like? And now I come to what we were talking about earlier about the self-duality and limits and co-limits. And I think yesterday, Marcello was asking about, in the category of DCPOs, you have this limit, co-limit, coincidence. Same kind of thing we want to happen in a Dagger category. So if I have limits of a certain shape, I automatically have co-limits of a certain shape, just by daggering everything. You might want to do things to coincide. So that's one of my desiderata for a good notion of Dagger limit. Suppose you're in a Dagger category, you have some diagram, you have two limit cones, then you can prove that they're going to be isomorphic, of course, because they're both limit cones. This thing is going to be a Dagger isomorphism, exactly when it's not just a morphism of limit cones, but also a morphism of co-limit cones. And that's something nice to have. So I think a Dagger limit should not just be unique up to ISO, but unique up to Dagger ISO. But this doesn't always occur. And here's two settings where you can see that. First, if you look at the simplest diagram you can think about, map it into category matrices over Compostela, say, a limit is just going to be an object n, together with an invertible n by n matrix. Right? Which is unique up to ISO. But you might expect a unitary matrix if you take this dogma. Second thing is, Amir Hasanovich was saying yesterday that we should embrace cycles, and I agree with that. Here's the diagram in the category matrices between the object 1 and 1. One matrix is multiplied by 2, the other matrix is divided by 2. Perfectly fine diagram, has a limit. A limit is just going to be mapped into either of the two objects, that is an isomorphism, so an invertible matrix. If it chooses which one, and they can't both be unitary, so if this one is unitary, then that one is twice the first one, so it will not be unitary. So some choice needs to be made. Alright, now I come to the fully general definition. What is a Dagger limit? So first, you pick a shape, and you pick a Dagger category that it's going to hold. I'm going to need to make some choices. I'm going to say a class of objects in the shape category is weakly initial if you can get to any object in the shape from some object in the initial set. Right? So some set omega is like the source, the start point of the diagram. Then I'm going to say a Dagger limit of this diagram together with that choice of initial choice. It's going to be an ordinary limit. I'm going to demand two things. First, that is normalized, so all the limit cones, all the cones or the morphisms of the limit cone, I want to be partial isometries in this sense. And I want them to be orthogonal, independent, like we were seeing for Dagger products. If I have two different morphisms in the limit cone, I want them to be orthogonal in that sense. This fits the things we had before. If you think about Dagger products, I can take this diagram, just two discrete points, and necessarily the weakly initial set has to be both of those points. And then this definition reduces to the one we had for Dagger products earlier. Same for Dagger equalizers. I keep it like an equalizer shape, just two parallel maps. For my weakly initial set, I'm just going to take the first one. I can get to any object in here starting from the first one, so that's fine. The first condition on normalization is then saying that the limit map into the first one is Dagger monic rather than just monic. And the second one doesn't say anything because there's only one object. Yes?
Where's omega used?
Oh, I'm sorry. These only hold. I should have said these two conditions hold for A and B and omega. Thanks. The last example of this, we haven't talked about this, but an interesting example is the Dagger splitting of a Dagger idempotent. So if you take an idempotent map that's even Dagger idempotent, I can make a diagram out of that by just looking at that self-loop itself and nothing else. Necessarily the weakly initial set has to be the one object that's there. What's the limit of such a thing? That's the splitting of the idempotent. What's a Dagger limit? It's a Dagger monic, a Dagger splitting. So it's a Dagger monomorphism into the object, such that if I go the other way around, I get a prediction. Alright, so that's Dagger limits. Now you can prove what we wanted, that if you have a Dagger limit of a diagram and any other ordinary limit of the diagram, the induced isomorphism between the two limits is a Dagger isomorphism, exactly when the limit is also a Dagger limit. It's a bit of a mouthful, but the conclusion is that the Dagger limits are well behaved in some sense. So first they're unique up to unique Dagger isomorphism, which is what we wanted. But also this weakly initial set that we have to choose doesn't play as big a role as you might think. You can make it smaller and still have the same Dagger limit. So you can sort of take, not just the whole diagram, that would be weakly initial, but really just the start points, so to speak. And vice versa. If you have a diagram, a weakly initial set, and a bigger weakly initial set, you can take the Dagger limit over the smaller one. If the bigger one also has a Dagger limit, then it's the same thing. So the dependence on this weakly initial set will be weaker than you think. Yes, I want to go through this. The next thing in your category theory textbook might be, now you know what limits are, how do you build them up? And typically there's theorems saying that if you have products and equalizers, you have them all. Again, that's not going to be the case here. If you have product and equalizers in the Dagger setting, you must be totally degenerate. And it's an interesting little proof. Because if you have finite Dagger products, then you can add morphisms. I can first take the co-diagonal. I can then take f plus g and then do the diagonal. Sorry, the other way around, diagonal and f plus g and then co-diagonal. And that's the way of getting f plus g. This should be very familiar to everybody in categorical algebra. That makes your categorics in commutative monomics. That's the finite case if you have arbitrarily big products. You're not just enriching commutative monomics, but in what's called sigma monomics. So that's why you can add infinitely many elements. If you have Dagger equalizers, you can prove that this addition is cancellative. So if x plus y is equal to x plus z, then y is equal to z. You sort of cancel x. But if you have both things, you can run the Eilenberg's window, take any morphism f, I can look at this infinite sum, 0 plus f plus f plus f, so same as f plus f plus f, same as f plus f plus f. But now we can cancel this part here, and hence f must be 0, so everything degenerates. So these kinds of theorems are really not what you would expect, and it just doesn't work. What you can do is, what's the right notion of completeness? So it's not having all Dagger limits, it's not having products and equalizers. The best thing we have, that I know of, and maybe this is right for improvement, but that's my challenge to you. You can talk about finitely based Dagger limits or Dagger completeness, in the sense that this weakly initial set is not just you can get anywhere from somewhere in the weakly initial set. There's a unique source in the weakly initial set that you can come from. I'm going to call it Dagger category based complete or finitely based complete if it has all Dagger limits for things with these kinds of choices. And then you can prove that this holds exactly when you have Dagger equalizers, finite Dagger products, and something called Dagger intersections, by which I mean you have a family of Dagger subobjects, Dagger monics. And what is their limit? It's kind of like with the Y pullback of all the intersections of subobjects. Alright, I'm going to skip this, because I want to talk about my favorite category of hope spaces. And this is the fourth and last act. So now we know all about Dagger categories, let's put it into practice and see what we can say about a specific important Dagger category. So just so we're all on the same page, by Hilbert space I mean either a real or a complex vector space that has an inner product in which it's complete in the associated metric. You can either take continuous maps or contractions. That's one to find Dagger categories, we were saying earlier. What does this thing look like? And the theorem I'm going to give you as evidence that these Dagger notions that we were talking about are correct in some sense is the following. If somebody gives you an arbitrary locally small category, it satisfies 6 axioms, then it must be this category of order spaces. And the point is, these 6 axioms are all about daggers. They're like elementary Dagger category theoretic axioms, have nothing to do with complex numbers or anything, it's just Dagger category theory. 3 of them we've already seen. The first one is that Dagger exists in the first place. The third one is you have finite Dagger parts. And the fourth one is you have Dagger equalizers. In the honest category Hilbert spaces, that means that satisfies these axioms because you have adjoints, you have orthogonal direct sums, and equalizers are closed subspaces. Okay, so that's 3 axioms we already understand. Fifth one is sort of the converse of the fourth one. So the fourth one said whenever you have 2 parallel maps, they have a Dagger equalizer, which is a Dagger monic. The fifth one says the converse in the sense that any Dagger monic is the Dagger kernel of something. In the honest category of Hilbert spaces, that is the case, because as soon as I have a closed subspace N of some Hilbert space H, you can always decompose the Hilbert space as orthogonal direct sum of that space and its orthocomplement. That's how Hilbert spaces work. And I can project out to the orthocomplement, and of course the kernel of that is going to be the injection into the first, into the subspace. So the category of Hilbert spaces satisfies this. I skipped number 2, because I'm going to slightly cheat there, and say in a minute what's the cheat. But it's similarly kind of weird, the Dagger thing. I'm going to ask that a tensor product exists. I'm going to ask that it is a Dagger tensor product in the sense that F tensor G Dagger is a Dagger tensor G Dagger, and all the coherence maps are not just isos, but Dagger isos. But I'm also going to ask something about the tensor unit. I want it to be a monoidal separator, meaning that I can tell 2 parallel maps out of the tensor product apart by testing it on vectors or global elements of these 2 objects. And I'm also going to ask that it is simple, in the sense that it has exactly 2 sub-objects. And in the category of Hilbert spaces, that's really just saying that your scalar field is a one-dimensional space. The only 2 subspaces it has is the 0 space and the thing itself. There's going to be a talk later in the afternoon by Mehdi Mehdiou that I'll promote now. It's really nice. That might say a bit about what happens if you drop simplicity. And in fact, you can drop the whole tensor thing. But for now, let's take this. Okay, so we know what axioms 1, 2, 3, 4, 5. Axiom 6 is I'm going to ask that directed coordinates exist. Not in the big category, but only of Dagger monomorphisms. So you take the big category, you throw out everything but the Dagger monomorphisms, and ask that that thing has directed coordinates. In the category of honest Hilbert spaces, that is satisfied because if you have a sequence of H1 is a subspace of H2 is a subspace of H3, etc., you can take the union of them all, close it off, and you get a nice Hilbert space, and that's the smallest one containing them all. Okay, so these are 6 axioms. Category of Hilbert spaces satisfies them. I'm going to, in the last couple of minutes, show you the shape of how you prove that any category satisfying these 6 axioms must be the category of Hilbert spaces. And the shape of the proof is a bit like this. You can reconstruct the scalars. So I haven't said anything about numbers, but you can reconstruct the scalars and show that they're the complex numbers. And from there show that these Hom spaces, Hom HI, they're always vector spaces over the scalar field. They take a particular form, it's called an orthomodular space, and then you can apply a magic theorem that says it must be a Hilbert space. So the point is to show that it takes this particular form. In the talk by Matt in the afternoon that I was saying, well, we'll get around this Soler theorem, because this is a bit of a magic black box that you can't really look inside, and there's a much more structural proof than that will show you. And it has a lot to do with what Paolo was saying yesterday about limits is limits. So Soler, this is a big theorem. She did that in her thesis. in 1970, I think, 1980s, somewhere about that period. And then she left math. She now works for an insurance company. And I was talking about this theorem before, and at some point somebody found her on LinkedIn, so now I'm buddies with her on LinkedIn, and we communicated a bit. And she sent me this email, and she was nice enough to give her permission to talk about that, because I wanted to point out this thing, which is really the way I feel about math. And maybe this is something for my younger colleagues. Sometimes you feel this connection. You're working on a topic from the 1960s, say the people are long deceased, that the work has sort of stalled in some sense, but still you feel like you're collaborating on it. You can pass something on. I really like that. And I'm looking at the time. I think I'm going to skip some of this. Yeah, why did I do this? So the first step was to reconstruct the scalars. We have the tensor unit, so you can look at the endo homestead. Of course, that's a mono 800 composition. It's also a monoid under tensor product in a second way by using the tensor product. And so by the Ekman-Hilton argument, it's not just a monoid, it can be a monoid, and these two multiplications of scalars coincide. You can propose them or you can tensor them, and it's the same thing. We already saw, because of the the Dagger product axiom is also monoid in a third way. You can add two such things. And the tensor product works well with this Dagger product. So now you have a multiplication on the scalars, you have an addition on the scalars, and the multiplication distributes over the scalars over the addition. So it's what's called a semi-ring, semi-ring. You can add, you can multiply, so you split. And through this all, by the way of the Dagger, you can take conjugates of anything. So there's an involutive structure on it. Then we're going to use the simplicity and the kernels to show that it's not just a semi-ring, it's in fact a field. So the trick is, if you have any morphism, you can always factor it as a Dagger epimorphism and then a Dagger monomorphism in this way. So this is a Dagger mono into the tensor unit that we know is simple. So it's either 0 or it's an isomorphism. If it's 0, we're done. If it's an isomorphism, then this thing is epi. If Dagger is a Dagger monic into I, so again that's 0 or iso. If it's 0, we're done. If it's iso, we're also done. Because that means that the whole scalar is invertible. So that way it inverses from multiplication. And then using the kernel axiom you can prove that we also have inverses for addition. So negatives. So it's actually a field, an analytic field. And we skip that, we skip this, we skip this. You prove, well, let me say a tiny bit about it. No, let me not, very clear of this, I think. So you prove in the similar kind of way using axioms that these home spaces on IH have the right shape to satisfy the hypotheses for Solaire's theorem. You apply your match theorem, and then you know exactly that the field is either the reals or the complexes or the quaternions. Can be the quaternions, but they're not commutative, so it has to be the reals or complexes. And you know that these specific home sets are in fact Hilbert spaces. You massage things around a bit, and you can say that any of these home sets are in fact the Hilbert space. So what we've done is shown that to any object of the category I can assign a Hilbert space. And from there it's relatively easy to show that this is in fact a functor. It's faithful, it's full, and it's essentially surjective, so it's an equivalence. And by hand you can show it preserves the Dagger and the tensor product, so it preserves all the structure of the axioms that I asked. QED, that's the theorem. Now for the last bit, let me say, so what have I told you about? I hope I convinced you that Dagger category theory is an interesting thing to do. It differs from ordinary category theory, and we saw some evidence for what's the right notion of monad, what's the right notion of limit, and how do you see this kind of thing. And how do you apply this to categorical algebra? Maybe I didn't stress this, but Hilbert spaces as a category is not abelian. I don't think it's semi-abelian or post-modular, but I'm not sure. But it's like a parallel kind of program you can do there. Not all of this is my stuff. I've worked on it over the years quite a bit. I've been fortunate to work with a lot of people on it. I've written writings with the word Dagger in it with all of these people. But the work today was mostly based on work with the top people here. Let me especially point out Matt, who's talking this afternoon. It's a great talk. You should all go there. Forget about differential categories. Stay in this room. And I will leave you with some references. Thank you.
Questions?
So, does it make sense also to look at limits of diagrams where the source category is a Dagger category and the functor is a Dagger functor?
Yes, that's a very good point. Thank you for making that. I should have pointed that out. If the shape category, the shape of your diagram, that category is a Dagger category itself, a lot of the theory becomes more smooth and you don't need many of the extra conditions for this limit code in the coincidence, for example. But this is a point I should have made in the beginning when I said you can't think about it as a formal theory of categories in DAG-cat. Then you would not be able to speak about equalizers, for example, because the equalizer shape is not a Dagger category. So that's, I think, a very good reason for not thinking about it as a formal type of category theory. Thanks, good question.
So I have a kind of a logical question. So I'm interested in, let's see, if you have a concept in category theory, do you feel like there could be some like a method of pushing that into a concept in this Dagger category theory? Or do you think that there is a fundamental like a difference? Like you already have limits in category, now have Dagger limits there. Do you feel like there could be a way of like finding the definition out of the categorical definition automatically?
I see what you're saying. I don't know of such a transfer theorem. There are some indications in that direction, which was free in the code-free constructions that I showed you of making a Dagger category out of an ordinary one. If you start with an ordinary category and a kind of limit in it, then you can often say something about the Dagger limit version of the code-free thing. So, for example, a class of Dagger limits that I didn't talk about, Dagger stabilizers. They're also important in this kind of completeness topic. That's a bit in that direction, but I don't know of a general logical theorem that says if you know this and this about categories, then you know that and that about Dagger categories. That would be interesting, but I think it might be hard.
Okay, another question over here. No, just one.
Firstly, thanks for the talk. It was very interesting. You said some stuff about monads and Kleisli and Eilenberg-Moore adjunctions. So those concepts can be also interpreted in two categories, in particular in the two category of Dagger categories. My question is, do you recover those notions, and also the comparison between Kleisli and Eilenberg-Moore in the ordinary setting is some kind of co-completion under you split co-equalizers. Is there a Dagger analog of co-completing?
Yes, so that's one thing you can do formally. If you take Speed's formal theorem monads and you run it in DAG-cat, most of that goes through, except that you need a notion of when Eilenberg-Moore objects exist. That becomes more intricate because now you don't need Eilenberg-Moore objects exist, but these Frobenius Eilenberg-Moore objects exist, and it's a bit unclear to me at least when that's the case.
We have time for, say, 2 more questions. I think Pino had one up here.
I was wondering, the next chapter in the book, or the next stage, would it be about the representable functors? What kind of a...
That's a very good question. That's one thing we actually looked at, but I don't have a good answer to that, because usually a representable functor goes into set, but set is not a Dagger category. So what is the Dagger analog of that receiving thing for free sheaves? And I do not know. But I would be very keen to know that. But as I said, we looked at it and I think it's hard.
Okay, one more. Actually, we're out of time, so you'll have to, after this, one more talk and then coffee break, you can ask Chris some more questions during that. So let's thank Chris.